So Beth and I both, she works at the BBC. She's a principal software engineer at the BBC, which I suspect in BBC terms is quite grand. I was far from grand, but I did work at the BBC for 10 years. And we've been enjoying reminiscing and talking about BBC culture, which doesn't seem to have changed a lot. It is a unique organization with its own perspective. So I would like you to give a GopherCon UK 2024 warm welcome to Beth Anderson.
Thank you. Hello, everybody. It's great to see you all and great to be back at another GopherCon. So in this talk today, we're going to discuss how AI affects you as Go programmers, or maybe more specifically, how AI will probably affect you. As compute power increases and new approaches make AI a mainstream technology, understanding their application and their influence is crucial for us all involved in technology. So in this talk, we'll debunk some common myths, we'll provide a candid look under the hood to reveal what these technologies are, and we'll talk a bit about how they work when we attempt to use them in our daily workflows. So why am I talking about AI, you might ask? Well, my name's Beth, and I work at the BBC, where I've been since 2009. I'm also one of the co-organisers for the London Gophers meetup, so I might have met some of you there. And I live in London on a boat with a small dog. So it might be helpful to talk a little bit about my personal history without getting too indulgent. My introduction to the field of AI was in the 90s when I studied computer science and artificial intelligence. And at that time, we implemented computer vision systems using Poplog, which was a development environment on top of the programming language Prolog. And that was used really for teaching and researching AI. So with this approach, we were building rules-based systems. The code that we ran to yield a result was written by us, other than the libraries we used. But the code, because it was written by us, it was easy for us to reason about and to understand. Much later, for my master's thesis, I focused on machine learning, utilizing a type of neural network called a convolutional neural network to classify audio sample waveforms. And the difference between this approach and that of my earlier university work was that this is a generated algorithm rather than a rule-based system. So by collecting together a set of audio samples, these could be labeled as particular types of sounds, and then a neural network trained on this labeled data to categorize new audio samples that the system hadn't seen before. It does this by using that type of convolutional neural network, which is an approach to classifying images without translational symmetry. In other words, some neural networks might struggle to identify a human face if they've only been trained on data in faces in a particular orientation. However, humans also sometimes struggle to recognize human faces in unusual orientations, as in this image where the eyes and mouth are inverted. So the thesis for this was that audio can be represented as a spectrogram, which renders audio as an image, and an image classifier could be trained on features of this audio. During my time at the BBC, I was one of the founding engineers at the BBC Datalab, and this is the team that the BBC, within the BBC that uses data and machine learning to help our audiences find relevant content. And at the BBC, we also have a responsible AI and ML team, and a surrounding community which focuses on how we can use artificial intelligence and machine learning in a responsible way, with thought to protecting data, and how content generation might affect content creators and even the impartiality of the BBC. And in this space, we have research into lots of areas, including appropriate use of AI technologies and tools, deepfake detection, which this is an example, and analysis of our own content, which is a vast amount of data. There's some links here for some of the BBC's public-facing information, but I can share those later on in the Slack channel. So I do need to say that I'm a software engineer. I'm not a data scientist. But this is why I'm speaking to you today, to talk from the perspective of somebody who writes code, who implements software to solve problems and to achieve goals. Now, I've been thinking of this talk for quite a long time, and when the conference call for papers opened, I was about to submit my talk proposal, which was going to be, will AI steal my job? But literally the day before I was about to submit my talk proposal, the excellent Go Time podcast released an episode titled, How Long Until I Lose My Job to AI? And also, at this conference, Adam Sholey brought his excellent talk, AI is Coming for Your Job, yesterday. So I had to rethink my talk. So after rewriting the proposal a little, I needed a new title. So I asked ChatGPT to suggest some based on the description that I'd written. ChatGPT has some suggestions, such as Beyond the Hype, Practical AI Insights for Go Programmers, Navigating the AI Bubble, What Go Developers Need to Know, AI in the Go Ecosystem, Opportunities, Risks, and Realities, AI in Go, Enhancing Code, Not Replacing Coders, and What's Up, Turning Humanity into the Ultimate Power Source. No, wait, I'm not sure how that got in there. Sorry. But it also suggested Decoding AI, a Go Programmer's Perspective, which I thought was a good title. So maybe ChatGPT and AI in general is good at naming things, which is definitely an issue that we have in programming. So to answer the question, will AI steal my job? Spoiler, probably not. But it's not that simple. So before we talk about details, we should clarify what we mean by artificial intelligence and machine learning. Some definitions we use within the BBC might help. Artificial intelligence, we consider a machine-based system that can perform tasks that are commonly associated with human intelligence, including making content, predictions, and other decisions. Machine learning we define as a technique which gives computers the ability to learn and improve at a task over time. And this is done by using mathematical and statistical techniques to identify patterns, to optimize systems, and to make predictions from data. This can be applied to solving different classes of problems, such as identifying objects in pictures, recommending TV programs, or even booking seats on a train. Another important definition is generative AI, and one that's arguably getting the most attention at the moment. So this is a type of artificial intelligence capable of generating text, images, speech, music, video, and code in response to prompts from the user. Examples include ChatGPT and Gemini for text, Midjourney for images, Gen 2 for video, and Copilot for code. So another important definition for us to cover is bias. Now, bias has a few meanings, or a couple of meanings, within machine learning, and it can be considered neutral or negative. However, the negative effect resulting from the use of AI is more accurately nowadays referred to as fairness rather than bias, to separate those two terms. But considering responsible AI, bias generally means a systematic skew in decision-making that results in unfair outcomes. This unfair outcome could be related to protected characteristics even, such as race, gender, disability, or sexuality. Bias can constitute illegal discrimination. There are a number of causes of bias, ranging from issues with data and algorithmic design to how humans interact with AI systems. Perhaps the most prominent cause is that AI systems trained to make decisions based on past data can replicate the historic biases of that data. So a really powerful example of bias coming from how humans interact with AI systems is covered in this excellent book, Weapons of Math Destruction by Cathy O'Neill. In this book, an example is given how a US police force used a model which was trained on past crime data to predict instances of future crimes and to deploy officers into those areas. So when officers were deployed into those areas flagged by the system, they found crimes being committed. So it would seem that the system was working, although these crimes were low-level crimes, the sort of you find in most cities, including public order and drug possession. In fact, if you drop police officers randomly in any city, it's likely they'd stumble across these kind of crimes already. But using a system to predict the crimes amplifies the recorded crimes in that area, creating a bias that these areas are more affected by crime than others. So it's important to consider the motivations behind this kind of analysis of data. Had the intention been to find hotspots of crime and instigate other interventions, such as investment in facilities and youth groups, the system is the same, but the outcome is different. So it's fair to say that AI at the moment is a buzzword, with loads of companies adding AI to products. But why now? So I think it'd be helpful to look at a little timeline of AI. So the earliest research into what would be later called AI was inspired by ideas that arose in the 1930s, 40s, and 50s. Recent research at the time into neurology had shown that the brain was actually an electrical network of neurons that fired in all or nothing pulses. By 1972, AI could navigate a room. Here at the Artificial Intelligence Center at Stanford Research Institute, researchers developed a robot nicknamed Shaky. Shaky had a limited ability to perceive and model its environment and could perform tasks that required route planning, route finding, and the rearranging of simple objects. However, by the early 70s, the tremendous optimism in AI research, which had raised expectations impossibly high, was dwindling as the promised results failed to materialize and the funding was reduced. So this led to what people would term the first AI winter, although many would say it really didn't affect the field of AI research, just funding to some large laboratories. But this is maybe even some foreshadowing to what we're experiencing now with the current AI hype curve. The 80s, however, saw a resurgence in the perspective of AI, including in the field of robotics. However, by the late 1980s, the bubble had burst again, and over 300 AI companies shut down, went bankrupt, or were acquired by the end of 1993, effectively ending the first commercial wave of AI. In 1994, H.P. Newquist stated in his book, The Brainmakers, that the immediate future of artificial intelligence in its commercial form seems to rest in part of the continued success of neural networks. And this is where my experience of AI started. And from my perspective, AI was a fascinating topic, although there was a feeling at the time that neural networks didn't really have that killer app they needed to succeed in the mainstream. But research continued, and by 1997, the IBM supercomputer Deep Blue had beaten the world chess champion Garry Kasparov in a chess match. And this was the first defeat of a reigning world chess champion by a computer under tournament conditions. So the idea that computers would struggle with complex tasks such as chess, but instead be able to make us cups of tea at home, was turned on its head when we realized that computers can be really good at rules-based systems, rules-based games, but struggle with real-world problems, such as working out where people keep their tea bags. In 2004, AI drove a robot on Mars, which helped humans deal with the delay in signals being transmitted from Earth. And in the early 2010s, Google developed AI to recommend YouTube videos. By 2014, Facebook was using deepface, which would correctly identify faces 97.25% of the time, which is just slightly behind humans, who can do it 97.53% of the time. In 2015, Deep Dream was released, and this computer vision program was another convolutional neural network used to enhance patterns in images, which simulates pareidolia, which is the tendency for perception systems to interpret ambiguous stimuli as containing a pattern or meaning when there is none. However, Deep Dream wasn't hallucinating or dreaming, but finding what it was being asked to, amplifying those signals in the input images. The original image here of some jellyfish was run through Deep Dream, which had been trained to perceive dogs, so after 10 and then 50 iterations. Deep Dream gripped people's attention because it was surreal, interesting, and actually really beautiful in a strange and creepy way. In 2016, AlphaGo versus Lee Sedol was a 5-game Go match between the top Go player Lee Sedol and AlphaGo, a computer program developed by Google's DeepMind team, which used neural Turing machines. These are neural networks that can access external memory like a conventional Turing machine. DeepMind won 4 of the 5 games. In 2018, DeepMind's AlphaZero learned the rules of chess in 4 hours by playing itself. And in the last few years, DeepMind's AlphaFold has been developed to perform predictions in protein structure. Initially released in 2022, ChatGPT is arguably one of the best-known AI products at the moment, even though the stable release was only on July 18th this year, only a month ago. So I hope you can see now that these technologies haven't come from nowhere, that they're not magic, but they're continuous improvements on ideas that have been around for getting on for 100 years now. So to understand a little bit more about AI architectures, we need to look at neural networks. So a neural network we often consider like a black box. You give it some input and it gives you some output. But the power, of course, in a neural network is what's happening within that box. So I have to say that most of what I'm going to say today is an oversimplification. But to get an idea of how these technologies work, it's good to start from simple ideas. Also, I'd really like to bust some of the perceptions that we're building magic software here, as some might think. While neural networks are complex, to say that we don't know how they work is a bit misleading. But some apologies for the simple examples here. So we could build a neural network to do our image classification. But let's take a look at what a neuron might look like inside of this black box. If we look at a simplified diagram of a neuron in a neural network, you can see there are some inputs which feed into some sort of summation. This is then passed to an activation function, and that decides if the sum of the inputs is appropriate to activate that neuron, and thus passing the signal on to the next connection, the next neuron. It could be that the sum is high enough or low enough, or some other characteristic. So of course these can be put together into a network of neurons, which as a sum of their parts can do much more nuanced and complex things. So taking this simple example, we could build a neural network to do our image classification. So we have a neural network here that is fired if the input is tail-like enough, and one that's fired if the input is furry enough. In a real system, the image itself will be encoded into a format much more appropriate for a machine. And to perform this type of task, we'd need a much more complex network of neurons. But in our simple example, we can give each neuron a score out of 10 relating to its input weight. And if the input is over 5, then the neuron will fire. So we have an activation on tail because we can see one of those. So that's quite confident, it's an 8 out of 10. And an activation on fur also. That's less confident, but still 6 out of 10. So still quite confident. So these combined weights activate the dog neuron. So our dog detector tells us, yeah, it's probably a dog. However, if we try a photo of a coin, we have an activation that it has a tail, but no activation that it has fur. So our classifier tells us it's probably not a dog. However, classifiers a little while ago struggled with some ambiguous images, and it couldn't always tell the difference between chihuahuas and blueberry muffins, or puppies and bagels, or even sheepdogs and mops. Even though you'll be glad to know that ChatGPT 4.0 gets this right, the reply is interesting, though, because it's slightly vague, saying that it appears to be a dog, likely a chihuahua. And this is maybe the creators of the model intending it to feel a bit more fallible, a bit more human in its replies, and less machine-like. So in these neural networks, typically, the neurons are organized into layers. Some are hidden within this black box. And these different layers apply different transformations on their inputs, which is eventually passed to the output layer. Neural networks are considered deep neural networks if it contains at least 2 hidden layers. It's this complexity that people will often say that it's hard to reason about, and that is true, but it's hard to debug a neural network due to its inherent complexity. Although it's possible to write a neural network yourself just with code, usually they're trained on real data, optimizing the difference between the predicted output and the target in a data set. And during training, neural networks learn from this labeled training data and attempt to minimize the loss between the actual data and the prediction, the loss being the mathematical price paid for an inaccurate prediction. So our dog detector neural network uses machine learning to perform classification, and a model which does this is called a classifier. There are many other types of machine learning techniques to perform classification, just as there are many approaches to generate content using a neural network too. So generative AI, it's certainly a topic of conversation as well at this conference, and we do have a lot of challenges, including how generative AI can be used to create problematic content or to use creative output as free training data. So we need to keep in mind that while AI is not all about generating code and images, generative AI is a really important part of the field of AI and is gaining traction in programming too. So let's look at a subset of AI you're probably already familiar with, and that is large language models, designed to perform language-related tasks. So in 2017, a paper by researchers at Google entitled "Attention is All You Need" proposed the transformer architecture, a deep learning architecture in which text is broken into tokens, converted into a vector, and then contextualized. Transformers were originally developed as a method of machine translation, but it's been used in many other ways since, including in generative pre-trained transformers, known as GPTs. So in a transformer, words are first tokenized. They're turned into numbers as a position in a dictionary of all of the words that the model handles. The tokens are then passed into an embedding layer and mapped into vectors, which are highly dimensional space, where each token occupies a unique location within that space. These tokens, of course, represent the words, and those words are related to each other. Those words that are related to each other are located close to each other in the embedding space, and the distance between words can be calculated mathematically. Token vectors also have positional encoding as well, which preserves the information about the word order, so the relevance of the word's position is not lost as well. So this allows the model to apply mathematics to understand a language. Maybe understand is doing some heavy lifting there. So these are then passed on to a self-attention layer, which are the weights that are learned during training. And these represent the importance with each word with relation to others in the sequence. The outputs of these are then processed through a feed-forward network, similar to the one we've seen, which outputs a vector of logits, which are non-normalized predictions that a classification model generates. These are proportional to the probability score for each and every token in the dictionary. And these logics are then passed to a layer called a softmax layer, and that creates probability scores for each word, and it includes a probability for every word in the dictionary. So ChatGPT-3 had 175 billion parameters, each at 16-byte precision, which requires 350 gigabytes of storage, as each parameter needs 2 bytes. And so from the information that's publicly accessible, but it's not confirmed by OpenAI, ChatGPT has about 1 trillion parameters, which could be 2 terabytes of storage. And these parameters relate to each mathematical link between words. So the more parameters the model has, the more options it has to put these words together. So essentially, the transformer can read vast amounts of text, detect patterns in how words and phrases relate to each other, and then make some predictions about how the words should be ordered and which word should come next, given some sort of input. An important innovation in modern transformers is this idea of self-attention. Words in a sentence aren't considered in isolation, but in a wider context. But also, transformers use some kind of randomness to create some authentic-sounding results, which is why you could ask ChatGPT or Gemini the same question over and over and get subtly different answers. Humans also can correct large language models in some cases, which is called reinforcement learning on human feedback. So why do we need to know all of this? Well, the reason I think it's important to understand is to understand how this process works, especially for us, if we're using these techniques to generate code. While there might be some who are looking to AI to replace people with magic software, AI can help us focus on the sort of coding that we want to be focusing on. But AI assistants now make a pretty good job of doing the average sort of tasks, the common sort of work such as generating mocks from interfaces. AI can also help you analyze your own code to detect bugs or performance issues. And AI can also analyze code and give you an explanation of what it does, as we saw yesterday in Liam's talk on Copilot. And also, AI can analyze large volumes of data from production systems and automatically generate incident reports in concise language, which Grafana does now. So a question we could ask is, do LLMs understand our code? Well, the term stochastic parrot was coined by Emily Bender to describe large language models. Stochastic in the sense that the output is randomly determined, and a parrot in the sense that the LLM doesn't really understand the meaning of the words that it's repeating. In response, Sam Altman, the CEO of OpenAI, later used the term ironically when he tweeted, "I'm a stochastic parrot, and so are you." But the phrase is often used to describe LLMs as pattern matchers, and it can generate plausible output via the vast amount of training data provided, parroted in a stochastic fashion. But the tendency of LLMs to pass off fake information might support this idea of a stochastic parrot. LLMs will occasionally synthesize information that matches some kind of pattern, but doesn't match reality. So depending on the data set, the LLM could actually generate some pretty strange results. For example, suggesting that you can add glue to pizzas to help the cheese stick. The source for this advice was a joke on Reddit, but the LLM wasn't able to determine it was a joke. Or the advice to eat 1 small rock per day. Of course, don't eat rocks. But if you ask ChatGPT how many R's there are in the word strawberry, it'll confidently tell you there are 2, even if you ask, are you sure? And this is ChatGPT 4.0 that's running now. If you ask how many R's there are in straw, ChatGPT knows there are 1, and that berry contains 2 R's. ChatGPT also knows that 1 plus 2 is 3. So even if we put straw and berry together, ChatGPT still sees my logic, but it still says there are 2 R's. So I'll point out again that there are 3 R's, and ChatGPT eventually agrees there are 3 R's. So ask again, and ChatGPT tells me there are 2 R's in the word strawberry. So it's a funny example, but it's natural language, and it's easy for us, or much more easy for us, to understand and spot errors. But code can sometimes take more effort to understand. And you can see the issue with fundamental errors being introduced into generated code. So we need to ensure that the output we're generating actually makes sense. And asking an LLM to generate an entire application is really too much to ask, because the output has a large scope. But generating smaller parts of code might be much more appropriate, such as mocks, tests, function signatures, and interfaces, etc. For average things that have been done a lot, LLMs can work pretty well. But as a thought experiment, I'd like you to think about how long it takes for you to understand all of your business processes in your organization to then write code. Because you're the link between those real-world problems and the code that we create. My own belief is that writing code is fundamentally a creative process. Maybe not in every case, but writing code is generally an exploratory process in which we begin to understand the problem space we're working in. So it could be about developing a solution which emerges through this process, rather than collecting together all of the colors of paint you need and just throwing them all at a canvas, expecting to create something in one action. It's fair to say that content creators are also suffering with content that's considered good enough, but being generated by models that is trained on the creative output that they are subsequently being excluded from. However, again, using these tools responsibly, we might supercharge the work that we do rather than replace it. Sven Vink, the CEO of the video game company Larian Studios, who produced the wildly successful game Baldur's Gate 3, said that AI is a tool that can help us do things faster, that we have so much work to do that we're happy to take assistance from anything. You might know if you play these games that you interact with many non-player characters, and the dev teams just don't have time to create all of the content for characters you might see, especially characters that have limited interactions. But using AI to generate the content based on the other work that they have done is a good approach. He said, I don't even think it will replace the creative side of things, and I can put my money where my mouth is. The question of using AI in creative areas is one that we all need to consider. On generative AI at the BBC, Rodri Talfan-Davies, the BBC's Director of Nations, said, "We will always prioritize talent and creativity. No technology can replace human creativity." So we've been looking at LLMs, which can generate output from within its own model. But as a contrast, evolutionary machine learning is a technique we can use to solve a problem from a starting point outwards, exploring a space we probably never experienced or a solution that's potentially never existed before. As an example, this is an antenna designed for a NASA spacecraft using a computer Darwinian evolutionary simulation, which evolved this shape of antenna by mutating the design and then checking how well it worked. Now, this is an unusual shape, and it's probably unlikely that a human would have thought of a solution like this, but an evolutionary machine learning algorithm produced it. So I don't want you to forget the incredible things that you can build with AI, especially solving problems which don't have an exact solution. We do need to talk about power, though. ChatGPT-3 took over 1,000 megawatt hours of electricity to train and requires 260 megawatt hours per day to run. ChatGPT-4 needs 50 gigawatt hours to train. And a Forbes article suggests that data centers supporting AI alone may well end up using a total of 1,000 terawatt hours annually by 2026, roughly equivalent to the entire annual electricity consumption of Japan, a country with 125 million people. Theoretical physicist Sabine Hossenfelder pointed out that one limiting factor in creating models may well be the sheer amount of energy required to train and run these models. So certainly ensuring green and secure energy should be a focus. On the other hand, the actual generally intelligent human brain only needs about 20 watts and can be run on pizza, so I think we've probably got some use yet. So from this talk, if you take away only a few things, I hope that we try and ignore the hype. Currently, AI is added onto everything to sell it to venture capitalists or to customer. The field of AI is fascinating, but the current hype bubble is rather artificial. In fact, we use AI and ML pretty much every day without noticing, from booking seats to streaming music. Because when products using these technologies become the norm, they're not really considered AI anymore, just software. AI isn't the best term, and it covers a lot of varying techniques and tools. It sounds good, but it I believe it sets us up to fail. And sure, there are some companies spending a lot of money to try and develop generalized intelligence, but pretty much all of what we're talking about could probably be more accurately termed generated algorithms, insofar as there are tools given training data to build us an algorithm. To be aware of bias in the systems that we build, it could be issues with data or algorithmic design, or how humans interact with the AI systems, or these AI systems trained to make decisions based on data which replicate historic biases. Above all, I don't want you to worry about AI. I want you to be involved in AI and to understand a little about what it is. But the truth is that I have no idea what will happen in the future, but I hope to be part of whatever shapes it. Because everybody's voice is important, and AI will surely affect us all. That's all I've got. Thank you.
Thank you so much, Beth Anderson.